Okay, so we have seen that how we derive the Gabor transform. So just to see it again, this term basically comes from this exponential. Okay. Then here we have to do now the Fourier transform of the signal, which is a Gaussian signal shifted in time. So there will be the contribution due to the time shift, which comes here. And then we have the Fourier transform of the Gaussian bell with this amplitude. So the Fourier transform of the Gaussian bell is given by this. Okay. So now the alpha that appears in this form is basically this alpha minus JB. So don't get confused I'm using the same notation for alpha here and alpha here. Okay. So we have square root of pi divided by alpha minus JB e to the minus omega squared divided 4 alpha minus JB. And this can be written as square root of pi minus alpha minus JB exponential of minus omega squared. We can bring the common denominator using 4 alpha minus JB. For alpha minus JB, I get minus omega squared plus we get the 4j alpha omega tau minus 4j alpha b tau squared. Okay? And actually, at the end of the day, now what we would like to do is to rewrite this Gabor transform. We are done, basically. This is the Gabor transform of the chirp signal, okay? But we would like to get the amplitude, okay? We would like to understand how this amplitude look like, okay? So we can plot it. And so we need to be able to, we would like to get xg squared, basically, okay? Which is equal to a squared. So let's see if we are able to extract it. But before to extract this amplitude square, before doing that, we can do a further simplification of this Gabor transform, and we can write it as x g omega tau is equal to. Actually, we got a very nice form, alpha minus JV. Exponential of what? You see that here we can bring these two terms together, at least because 4j and tau and alpha, 4j alpha and tau from here. So we have minus omega squared plus 4j alpha tau, which open parenthesis omega minus beta tau divided 4 alpha minus JB. And believe it or not, this is the Gabor transform of x of t equal e to the j bt squared. Very nice. It's a very nice formula. No, it's not that bad. Now we would like to plot this. We would like to learn something out of this transform. Okay. We would like to understand how this short time Fourier transform works, and because we already have an idea about the signal, we know that the local frequency is equal to what? Is equal to the derivative of this guy. So is 2bt. So we have a local frequency that is increasing in time. And so, since the window here is constant, what happens? We expect something like this. So we have, this is our chirp signal. So, when for a given alpha, when tau is very close to the origin, so the Gaussian window is still the same, right? So, and here I should have done it a little bit later. And then when we have a later time, the Gaussian window is still the same. Okay? So what's going to happen is that what happens is the following: that for short times we will have bad resolution in frequency because the window is too short and is not able to detect the long frequency components. Okay, but when tau is very large, the window is going to be large enough to be able to detect the oscillations, the fast oscillations. And so on, and when the wind for very large time, the accuracy become better and better, because the signal, the frequency become larger and larger, and so when t become very, very, very large, this frequency, the local frequency, is very, very, very large, and so this window is going to be almost like an infinite window. Let's see if we can see this trend in this Gabor transform. So I expect this Gabor transform to be localized around this local frequency, and then with a spread that decreases as the amplitude, as the tau variable increases. Let's see if that is true. But in order to do that, we need to extract the amplitude. Let's try if we can. I would like to extract, xg of omega tau equals a of omega tau e to the j phi of omega tau. Okay, this is the Gabor amplitude and the Gabor phase. Okay, we would like to derive this quantity. I don't care about this part for now. Okay, so let's see. And at the end of the day, the important part is going to be this exponential, okay? So a of g omega tau, more or less, you can see from here, is going to be the modulus of this guy, which is basically, square root of pi divided alpha square plus beta square a quarter. Okay, and now we need to work out this exponential. Okay, so what I'm gonna do now, I'm gonna multiply and divide by alpha plus j beta time, and all of this times alpha plus j beta. That's what we're going to do. Okay? If we do that, the numerator becomes 4 alpha square plus b square, pretty standard. The numerator, we have this multiplication, so we have to be careful. Let me rewrite it. 4j alpha tau omega minus b tau, which multiply alpha plus jd. Okay, so, and of course, when I do this multiplication, I simply have to retain only real values. Okay, I don't care about the complex values because they will go and form the phases. Okay, so if I do that, we see the dependency here is gonna, more or less, the dependency is gonna be 1 over square root of alpha times exponential. Now, when I do this multiplication, I get 4, which multiply alpha square plus b square, and on the numerator, when I multiply alpha times omega square, I'm going to get a real value, which I'll keep it, alpha omega square. When I multiply alpha times this other term, I'm going to get an imaginary term. I don't care. It will form the phase here, but I just worry about the amplitude. And then I have this JB times this, it doesn't, I don't care, it gives me an imaginary part. But then when I do this times this, I'm gonna get a real number. So I'm gonna get j times j, it becomes j squared minus 1. I'm gonna get minus 4 alpha b tau, which multiply omega minus b tau. Okay? And more or less, this is the story, actually. Okay, so actually, what, to be precise, let me keep the entire dependence. Okay, so I'm gonna write alpha square plus b square a quarter. Okay, and you see that we can still do some simplifications, because I can bring the alpha outside, and you will see some surprises now. Because I think I did the math correctly. I hope it looks like, because I expect we're going to get something that maybe now is correct. So I can bring this alpha in common. So we have exponential of minus alpha fraction 4 alpha square plus beta square. And then on the numerator I'm left with omega square minus 4 omega beta tau plus 4 beta square tau square. Okay? You can see from here. Minus 4 beta omega tau plus minus minus plus 4 beta square tau square. Okay? And it's very interesting to realize that this term here, these three terms here, they are what? They are omega minus 2 beta tau squared. And that's pretty good. So you will see now why. I think you already realize it. So this 2 beta tau is the local frequency. Okay? And it comes naturally from omega square plus 4 beta square tau square minus the double product 2 times 2, 4 omega beta tau. That's very nice, because we finally have the final expression for the chirp of the amplitude of the chirp signal, which is proportional to 1 over alpha square plus b square a quarter. And then I have this exponential of minus alpha divided 4 alpha square plus beta squared times omega minus 2 beta tau. And now we can do we can plot it, because this it looks like a Gaussian as a function of omega. This looks like a Gaussian. Remember, the Gaussian is going to be something like e to the minus s squared divided by 2 sigma square, if I plot it in the s domain. And the bandwidth is, and the standard deviation is basically given by this quantity here. So in our case, as a function of omega, okay, so we derive this nice expression of the amplitude of the Gabor transform of a chirp signal. And now we would like to, to see how it looks like in the omega tau domain. And it's easy to recognize that for a given tau, this expression is basically a Gaussian exponential in omega, and it's going to look like something like this: e to the minus omega naught squared divided by 2 sigma square. And we know that for a Gaussian exponential, this is, of course, in general, we have 2 pi sigma square. if we think about a PDF of a Gaussian distribution. So omega naught is the mean value, which is going to be this, and then the standard deviation is given, it is here, okay? And the sigma square, this is the variance that gives me the spread around omega naught by sigma plus sigma, omega naught plus sigma, and omega naught minus sigma. And here, these are the inflection points where the curvature changes. Okay, so it's easy to realize that I can rewrite this exponential as ag omega tau is going to be proportional to alpha square plus b square quarter exponential of minus, gonna have omega minus 2 beta tau squared divided, I borrow a 2 from this 4, and then I can rewrite this term as alpha squared plus beta squared divided by alpha. I bring this alpha down. So now identify my my variance sigma squared, the spread around the mean. So now we can see that I remind you that what is this 2 beta tau? This is the local frequency, which is equal to the derivative of the phase, which was is 2bt. Remember that the signal is EGBT squared. So this is the phase that I use here. The time derivatives gives me the local frequency, which is exactly what we have here. And this is basically, the spread around the mean. So what I learned from here, so I have a diagram. So I have the diagram tau as a function of omega. Here I have the line, the linear frequency 2 beta tau. And what is interesting that at any given tau, we get a spread. It's a Gaussian distribution, and the spread basically, is gonna give me is constant. You see, the spread around this mean is constant. It doesn't change with tau. But as you can see from this diagram, from the Gabor transform, we were able to identify the change in frequency of the signal, because the original signal was this. So it was the chirp signal, okay, or at least the cosine part. So of course, if you're gonna also add the other, if you add also the other component of the cosine, you're gonna get also the negative frequencies, okay? And as you can see, the variance, this spread is equal to the square root of alpha plus beta squared divided by alpha, okay? And so when you can basically compute it. And so as you can see, thanks to the Gabor transform, we were able to get this